Hi, in this video, I'm going to talk to you about the control exercise 2025 in the course materials section of design project BEng chemical engineering module that I'm currently taking. So let's give it a go, shall we? So I'm going to expand this tab to full screen and talk to you what this is about. Yes, control exercise 2025. You are supplied with a flowsheet for the design of a continuous process plant to be built by Rex Chemicals as a separate document in Surrey Learn. The process is to make liquid product C, whose purity is approximately 99.3%, from a gaseous reactant A, supplied from unit J at 5 bar and 30 degrees Celsius, the flow of which you must take at the rate at it is supplied, and from unit K, liquid reactant B at 160 degrees Celsius, supplied at the presence of 6 bar, whatever rate you wish to take. The feed from unit K contains 0.2% of D, which is inert over the heterogeneous catalyst used in adiabatic packed bed reactor R1. The feed from unit J contains 0.5% of nitrogen, which may be regarded as inert. And the reaction is equilibrium limited and takes place at about 300 degrees Celsius over a heterogeneous catalyst, whose reaction is as follows. 1 mole of A plus 1 mole of B, two reactants mixed together to form a product, 2 moles of C. And additional conditions are here. The reaction is mildly exothermic. Bracket, the temperature change is about 30 degrees Celsius, and a 25% excess of B is used to ensure at least or minimum of 99.5% conversion of A, thus simplifying the separations part of the process. The feed to R1 is heated to 285 degrees Celsius by heat exchange with a hotter reactor effluent in E2. The reaction temperature is controlled by bypassing some of the effluent around E2. The effluent, now cooler, is partially condensed by the cold fluid from unit J in E1 and then distilled in V1 with the overhead vapor being partially condensed in E3. The liquid top product is separated from the mostly uncondensed A plus C vapor in different scenario. In reflux drum V2, where A and C are flammable, but C is mildly toxic, and so the gas stream, containing most of the nitrogen that comes with the feed from J, is sent to an incinerator operating with an input pressure just below atmospheric via a vent condenser E7 and a knockout pot V4. The liquid separated in V4 flows under gravity to join the main liquid product flow from V2 to the atmospheric product tank T3 via refrigerated cooler E6. For safety reasons, C must be stored at or below at normal boiling point of 18 degrees Celsius. On warm or hot days, heat gained by the tank from its surroundings causes boiling, and the vapor so produced also flows to E7. Wait here. This is just a brief overview description, so I'll press the escape button and then display this what the Visio flowchart look like. So I'm going to explain what early description has been applied to this production plant complete flowchart in Visio form. Yeah, Microsoft Visio form, to be honest. Here, steam header and refrigerant vapor return header all are coming out as feed, and then some gets like entered here to E4 and E5 respectively. Also mentioned here, unit G and K has variable amount of product A, B, and C that depends on how much proportion is converted to the desired product. To E1, this is to E5. Some of the components get mixed together in reactor, this R1. Some goes to the distillation column V1 here. Of course, this distillation columns, theoretically, what shall I say? It separates the vapor distillate in this condenser E3 as well as reboiler stage in E4 underneath it. Also pass through the vessels respectively here V2, V4. Also changing pressures like using these operating pumps like P1 and P2 that come in or flow from the distillation column or these vessels respectively. Change optimal temperature, go to heat exchanger like E6 or E7, or it either rejoins back to the feed stream product or store in this tank T3. Remember the variables given with temperatures and pressures, what has to be optimized here. So considering here is very important. Underneath as well, after scrolling down, refrigerant supply header also provides some components flow through, for example, goes to E6 heat exchanger, then travels either different components or storing the tank for optimal usage. For example, some components in vessel V1 is flow out as purged waste system. Like these products, you have to determine whenever you create this design project coursework process together, either individually or in groups. So I click the escape button and go back to here to complete the description. I'll just maximize it a bit. So if I scroll down, let me finish reading this up. Most of the liquid falling from the bottom tray into the sump of V1 flows into a thermosiphon reboiler E4. You just notified it, the reboiler stage. Mostly unreacted B with C and D in lower concentration. Some of the liquid is purged, less D build up and cause the production rate to decline. E4 is driven by steam. Rest of the liquid containing unreacted B is recycled via centrifugal pump P2 and the thermosiphon vaporizer E5 or V3. Utilities available are shown here. Electricity, atmospheric air whose maximum temperature 28 degrees Celsius, or refrigerant with a boiling temperature of 5 degrees Celsius, and finally a steam with a saturation temperature of 180 degrees Celsius. Is given the question that you are required to devise a control scheme using the three-term style of control loop taught by Dr. Thorpe. Like example, don't use the PNID style of the POM module. Okay, just ignore this. Each correct control loop will attract 2 marks for the parameter measure, 2 marks for correct position of measurement. In this case, cycle with $C written inside it, 2 marks for an adjustable element that affects the thing measured. However, unnecessary controllers will attract -1 mark. Okay, might be critical penalty applied to some who didn't know how to apply this control loops, so penalty might punish them. Also estimate the pressures and temperatures on all process lines in the recycle loop from V1 back to V1 via V3 and R1. Also assume 30 real plates below and 30 above the feed in V1, which has a drop pressure of 1.2 bar. As well as the pressure difference guidelines of delta short may be used. Okay, just ignore that as well. There will be 1 mark per pressure and 1 mark per temperature correctly added. Assume a height difference of 10 meters between level in the sump in V1 and that in V3, and that the density of liquid streams in this process is 850 kilogram per cubic meter. Let me scroll down. You are reminded of the laws of fluid mechanics. If you leave a pipeline open, a large flow will go through it. If a fluid has the choice of 2 paths, one with a small equivalent length and one with a long equivalent length, most of the fluid will follow the path of a short equivalent length. Delta P's must be seen down in either pathway. One consequence of having to provide NPSH is that you must not place any unnecessary pressure drops in the pipework feeding to a pump. This includes placing control valves in this flow when they can be placed downstream. For example, like this map. This one to not necessarily needed whenever you scan this, but have to learn by heart. Let me finish this off. So here, composition controllers are expensive and may be unnecessary for this control scheme because suitable proxies can be found. If you wish to use a composition controller, you must specify exactly what you're measuring, example, concentration of component D, and what the sensor technology is. You must specify things that can be measured online, example, attached to the process and in real time at reasonable cost, like, for example, temperature, pressure, flow rate, thermoconductivity, electrical conductivity, pH, light transmission, or UV absorption. However, mass spectrometry is not allowed. Also given here, you may be tempted to add too many controllers, allow fluid mechanics to do some of the work, like example explained here as a vent connected to the atmosphere ensures a just above atmospheric pressure zone. Storage tanks do not have level controllers, do not show steam traps, they assume on all flows going to the condensate return line. Just ignore this statement, I'm not going to read it out, so let me finish this off in the last few minutes. Devise a control scheme for the Rex Chemicals flowsheet and turn your proposal into a PDF or a JPEG. Okay, this important statement in bold text, I mean. Add your name and or URN at the bottom left-hand corner. Add control valves or either adjustable elements to the diagram as necessary. Block valves used for equipment isolation should not be shown. Also, remember to submit your answer to the assignment folder on StoryLearn by 4 p.m. Not this day on Monday, but will be given in an assignment date, so I will preview that later on. Note that your submission must be legible, so scans of handwritten answers must be good quality. It is your responsibility to check the legibility. Finally, your mock exercise will be made available to you within 3 weeks. This should help correct misunderstandings about control schemes for whole processes, which will enable you better to add a control scheme to your area. Requirement of the process design report. The end. Every single description of control exercise 2025 have been given, so let me go back to Visio diagram for a moment. If I zoom it in, yes, the last statement I've spoken, like some components in E1 flow go through to distillation, column V1, reboiler E4 or condensate part E3, other storing tank or return to feed products. Some unwanted components somehow get pressurized, increase pressure by using these centrifugal pumps in P2 and go back to this recycle stream, return the process. Entire system repeats itself like you call like a control loop. You have to add them up. I'll show you what the answer may look like. For example, if you click on this, and I'll explain you how each works. For example, you see with this mouse, this is FFC, feed flow controller. So attached to from unit K, measure how much feed flow rates might be traveling at a particular time. Measure here, so attached to both here, I think, and this as well. E1 to E5, 2.5 bar, 145 Celsius is given the question, so it might be somewhere around the area, as well as temperature controller around the bypass that returns to E1 from after reacting in the reactor R1, the temperature control, just how much temperature has to be maintained consistently or optimally throughout the entire chemical production reaction, as well as lots of temperature controls around the distillation column here and there, also in the vessels here and there. Oh yes, note that LC is level controller, so it might not function the same thing, but you have to watch out for it. Also connect with these feeds like FFCs and TCs. Just the examples of answer briefs how each controller works in this first place. So yeah, just one more thing. So going to preview what this assignment is going to be like. So I'll click on this assignments. Yes, this is about process control coursework. Using both these test files, which I already downloaded them a few days prior, is due on the 20th of February, so 10 more days to go. Today is the February 10th, submitted by 4 p.m. on that day. If I click on this, yes, C course materials, process control, I've already viewed it. I think 20th day is on Friday, 4 p.m. That week 3, end of week 3 deadline. Yeah, upload files and submit, but here are the instructions, but I'm not going to read them out loud because I've already read too much in this video content already. So like you may add optional comments to explain and add files to submission. Then before pressing the submit button, that you confirm that assignment has been submitted by yourself, and very successfully without cheating or any other copyright laws created, like for example uploading YouTube content from a particular video creator. So have to deal with the same submission and regulations in the first place. But anyway, that's it all for this today's video explaining how my control coursework should be going well. Hopefully I might be able to finish well before deadline if I know how to deal with this right. So good luck to me myself actually. Anyway, that's it all for this video, guys. Time is running out. Bye for now.